Hello everyone, this is Chengzhi Wu and Hao Fu from Karlsruhe Institute of Technology. The topic of our presentation today is 6D pose estimation on point cloud data through prior knowledge integration, a case study in autonomous disassembly. In today's context, within the framework of life cycle engineering, the importance of end-of-life strategies has been heightened due to growing environmental concerns. As one of the end-of-life strategies, remanufacturing salvages the efforts that were initially used to shape the product and presents opportunities for creating further business profits. In contrast to traditional manufacturing, remanufacturing is challenging due to the complexity, uncertainty, and inconsistency of the returned products. Consequently, the primary processes in the current remanufacturing are still carried out manually. In order to automate this process, a flexible and adaptive system is required. The AgiProbit project focuses on such automated disassembly system of end-of-life electric motors. The project aims to design an agile remanufacturing production system in order to react dynamically to uncertain product specifications using artificial intelligence. An interdisciplinary research group from several institutes from mechanical engineering, electrical engineering and information technology as well as computer science, is collaborating to specifically bundle their complementary skills. Our team concentrate on the disassemble process of the starter motor. The processed starter motor is clamped and disassembled by a multifunctional robotic arm. Concerning the bolts on the motor, besides part segmentation, accurate 6D pose, which encompasses their 3D position and 3D orientation, is essential to facilitate the robotic arm spatial movement to the correct position and ensure its disassembly movement in the correct direction. However, due to cost and space constraints, the 3D camera is installed in a fixed position, which can provide only single viewpoint clouds. Meanwhile, under the rigidity and stability requirements of the lamping system, the motor remains in a random but immovable position during the disassembly process. This results in low-quality scanning or even view occlusion of numerous critical features, such as bolts on the complex motor. In this paper, we propose a multi-stage pipeline to compute precise bolt 6D pose even under these unfavorable conditions with integration of prior knowledge from multiple information sources. For example, in another team of our project group, the full model of the stator motors are scanned and serves as part of our prior knowledge. As illustrated in this figure, our full pipeline consists of 5 stages. Binary segmentation on real-world scene point cloud. Registration between 2-point clouds. Part segmentation on the extra input of full motor point cloud. Normal alignment for bolt orientation. And bolt point clustering for bolt position. During remanufacturing, a single viewpoint cloud is captured by a Zivid camera. The single viewpoint cloud is passed through a deep learning model, which distinguishes between the clamping system and the motor. Using the point cloud of this motor as the target and the full motor point cloud as the source, a registration process is executed, resulting in a transformation matrix from the extra input coordinate system to the Zivid coordinate system. The full model point cloud of the starter motor, which is obtained through a scanner, is acquired as prior knowledge in this study. The extra input full model point cloud is first fed into a deep learning model that segments it into 6 semantic parts. The orientation of bolt is determined based on the orientation of the full motor. Prior knowledge suggests that the orientation of the bolt can either be the same as or opposite to the orientation of the full motor. However, the full motor point clouds are typically from different sources or scanned in different positions, which means the orientation of the full motor is unknown. Therefore, a segmentation result-based normal alignment method is proposed, allowing us to align the motors to obtain their respective motor orientation and determine bolt orientation accordingly. The 3D positions of the bolt CT bolt is represented by the clustered centers of individual bolt point groups in the segmented full motor point cloud. For this study, we have access to only 18 starter motors from a series. To obtain a full model data set, we utilize a T-scanner to scan the motors. However, these data sets proved insufficient in terms of size and representativeness for our segmentation task. The allocation and annotation of significantly larger data sets are both costly and time-consuming, rendering it infeasible. As an alternative, we turn to synthetic data sets generated by a Blender add-on called Motor Factory. This add-on initially creates a substantial number of motors with diverse specification outputs them as synthetic full model point clouds. A point cloud transformer network for part segmentation is initially pre-trained on the synthetic full model point cloud data set and then fine-tuned on the real-world full model point cloud data set. Here is one of the scanned point cloud and its segmentation prediction. Subsequently, the motors are secured in a clamping system in accordance with the remanufacturing process requirement. They are scanned by a fixed Zivid camera. And a real-world single-view dataset is obtained. Similar as part segmentation, the add-on, Motor Factory, synthetic single-view point clouds with clamping system from various viewpoints. The point cloud transformer network for binary segmentation is pre-trained and fine-tuned on their corresponding synthetic and real-world dataset. Here is one of the scanned single-view point cloud and its binary segmentation prediction. For registration, we use a multi-step method. We divided our approach into two steps, coarse registration and fine registration. In the coarse registration step, we downsample the point cloud, estimate normals, and compute a 33-dimensional fast point feature histogram FPFH for each point. The FPFH feature comprehensively describes the local geometric properties of a point. These features are then employed in fast global registration. For the fine registration step, we employ iterative closest point, ICP. As we reduce the maximum matching distance Dmax, the likelihood of false matches decreases, yielding a smaller registration error. After the described part segmentation, the point cloud is segmented into bolt and 5 other classes. Given our prior knowledge of the motor structure, points belonging to the same bolt should be grouped together, while those from different bolts should be separated. However, the precise number of bolts on the scanned motor is unknown. Additionally, there exists a certain level of noise, and the shape and size of the bolt point clouds can exhibit variations. These characteristics make the density-based spatial clustering of applications with noise algorithm, dbScan, exceptionally well suited for this task. We utilize the dbScan algorithm to cluster the bolt points into distinct bolt point clouds, with the centers of these bolt point clouds representing the desired 3D positions. The alignment of the full motors is as follows. Based on the segmented full motor point cloud, we obtain the normal vectors for each point on the main housing part. These normal vectors are represented as points in space, as shown in the bottom left figure. It can be observed that these points form a spherical surface, which is most dense near the equator of the sphere. This equatorial plane corresponds to the motor's Zoi plane and is determined by Ransack. With this plane as a reference, other orientations can be determined. Z-axis is defined perpendicular to Zoi plane. The positive direction of Z-axis is determined by the relative position of centers of main housing and connector. Y-axis is deigned to coincide with the projection of the line connecting centers of main housing and solenoid. Finally, X-axis can be determined by Z and Y-axis. We conduct experiments on 2 ICP variants, one based on point-to-point matches between the source and target, and another relying on matches between points in the source and planes in the target, which are determined by the points and their normals. Additionally, we test several combinations of maximum matching distances. The results are presented in this table, which demonstrates that as the number of fine registration steps increases, processing time exhibits linear growth, and registration accuracy improves significantly. Furthermore, compared with the point-to-point algorithm, the point-to-plane algorithm exhibits notably reduced processing time. In this study, although real-time performance holds importance, we prioritize precision over real-time performance, leading us to choose a point-to-plane registration approach with 3 fine registration steps. More experiments are conducted to identify the most suitable combination of structures and algorithms. Given that our test set comprises only 18 motors, which is extremely small, the results derived from a single train test split setting lack representativeness. To mitigate this issue, we use a method of cross-validation. In each training, 2 random motors are selected as the test set, and the other 16 motors are used as the training set. We perform such trainings 5 times and report their mean results as the final cross-validated performance. 4 widely used backbones are evaluated in our experiments, as depicted in Table 2. We find that the point cloud transformer yields the most favorable results. Following this, we conducted tests on various hyperparameters based on the point cloud transformer, and the most significant experimental results are presented in Table 3. Note that all the experiments in this table use the aforementioned cross-validation. Moreover, for a fairer comparison, we make the 5 train test splits identical for all the experiments. From it, we can observe that the effectiveness of performing pre-training on the synthetic dataset is evident. To mitigate model instability resulting from an excessively high initial learning rate during transfer learning, using a warm-up strategy can further optimize the performance of our network model. Regarding the input subpoint cloud size for the training, as indicated in the Table 3, a sampling size of 2048 points performs the best, even better than a sampling size of 4096 points. Since increased sampling size leads to a reduction of the actual interaction steps in one epoch, an additional experiment of 4096 points with doubled training epochs is performed. However, its performance still does not surpass that of the one with 2048 points. The video illustrates an example input point cloud in a real-world case. The red arrows depict the computed 6D pose of all 9 bolts. As shown in this video, our method can accurately determine the 6D pose of bolts, even in cases where they have not been precisely scanned or are occluded. In conclusion, this study presents a novel pipeline designed for bolt 6D pose estimation by utilizing a pre-acquired model, part segmentation, normal alignment, and bolt point clustering to extract valuable information for 6D pose estimation. The experimental results illustrate the effectiveness of our pipeline even in challenging cases characterized by low-quality scans and occlusions. Finally, we would like to invite viewers of this video to take a virtual tour of our lab. Through this website, you can learn more about the works of the AgiProbot project. We would love to communicate with researchers from all over the world. Thank you for watching.